We live in an infinite and expanding universe. Space has no edge. It goes on forever. But there could be a different kind of edge to our universe, an edge of time.
The universe seems to have begun 13.8 billion years ago in the past, so there's some inclination, some impression that it's finite in time.
What we call the Big Bang is, as far as we understand it, a beginning, a start of the universe. The universe has a finite age. Now, does it have an edge in the future?
We used to think that time would someday come to a catastrophic end, along with the planets, galaxies, and all life in the universe.
If we know there's a Big Bang, if we know the universe started, expanded, and cooled, it's very natural to wonder whether or not someday the expansion will stop, reverse, and come back. And that's a big crunch.
In a big crunch, our expanding universe would begin to contract. Stars and planets would smash into each other. Galaxies would collide. And all of the life left in space would be compressed with all the other matter into a singularity. If this theory is true, then the universe would have both a beginning and an end of time.
If we live in a universe that will expand, stop expanding, and then go back into a crunch, then it has, in effect, two edges.
But there's a much stranger possibility.
Perhaps the end is but a beginning. Well, the universe is an oscillating universe. It has a Big Bang-like beginning. It expands to a maximum size and then goes back into a big crunch and does that over and over.
We could be residents of a universe created from the ashes of another, a single universe in a stream of bouncing universes. Each full of galaxies, planets, and life. But our most recent observations of the universe suggest a big crunch isn't in the cards. Once again, dark energy is key.
For a while, we didn't know if the expansion of the universe was going to slow, stop, and reverse itself because of gravity. There are all these galaxies in the universe, and they're pulling on each other by their gravity. And if the expansion isn't fast enough, that gravity might be strong enough to stop the expansion and recollapse the universe. Now, with dark energy, we know that there's no way that can happen. The universe is going to expand forever because dark energy is pumping it full of acceleration.
In order for there to be a big crunch, our understanding of dark energy would have to change a lot. That is, dark energy would have to be extremely weird and turn off in some very funny way for the universe to suddenly stop expanding and recollapse.
Without a big crunch, there is no future edge to time.
The universe is not only expanding, but it's being driven by dark energy to expand faster and faster. And the dark energy doesn't dilute away, as far as we can tell. So the simplest idea is that the universe will simply continue to expand eternally toward the future.
Just like space, time will go on forever. That might sound like a better fate for life in the universe, but it's not.
One of the consequences of this dark energy that's causing the acceleration of the universe is that we eventually are headed towards the big chill. I should say we're eventually headed towards the big chill. So the universe is getting colder and colder, and things are getting more and more spread out.
So the accelerated and continual and forever expansion of our universe might make for a frankly depressing end to time itself. The ultimate entropy-based heat death of the universe, where you would walk out and see no stars in the sky. See absolutely nothing. There will come one day when the very last star in the universe just fizzles out, and that is it.
In the future, space will be a cold, dark, and infinite void, where time goes on forever. There will be nothing to do but suffer in the eternal expanse. It's our inevitable fate that there's no future edge of time in the universe. But even if there isn't an edge to the universe, could there be edges within the universe?
If you wanted to visit the edge of the universe, then go find your nearest black hole and jump on in, because that's a one-way trip.
If you cross this edge, you will never return. April 2019, an international team of astronomers makes a special announcement.
And we are delighted to be able to report to you today that we have seen and taken a picture of a black hole. Here it is.
It's a picture of a supermassive black hole at the center of the M87 galaxy, 54 million light-years away. It may also be the first image of an edge in the universe.
Black holes create a really interesting scenario when we think about space and the universe having edges.
The edge between space outside and inside a black hole is called the event horizon.
The event horizon of a black hole is a region within which, once you cross inside, the gravitational tug is so strong that even light cannot escape, which means nothing can escape once you cross inside the event horizon. So that really is sort of an edge, because it really does create a boundary.
The event horizon is not a physical barrier in space.
The event horizon is an edge of the part of the universe we can visit. But it's not an edge in the sense that there's anything there. You would just pass right through it if you actually got right up to that place. So it's sort of a conceptual boundary between two different parts of the universe.
If we sent a manned probe into a black hole, it would be a one-way trip.
The event horizons of black holes are a sort of edge, because once you pass through an event horizon, you are cut off from the rest of the universe. You can never go back out. You are outside of our universe.
Once you've crossed inside that region, you are never coming back out. And that's an edge.
Once inside the black hole, the probe would be in a separate part of space, cut off from the rest of the universe.
Falling through the event horizon of a black hole is like jumping over the edge of a cliff. You can see the edge, and you can see the edge go by, and then when you're at the bottom, you can look up and see what's happening at the top of the cliff, but you can never go back.
At the bottom of this black hole cliff sits a singularity, a region of space where the laws of physics go off the rails.
Deep toward that singularity could be as surprising as you might imagine, and yet still a possibility.
If you map the space-time around a black hole in a very particular way, there emerges a sort of mirror universe, a parallel universe on the other side of the black hole, identical to our own, and traversable via the black hole.
So black holes are not just edges to our universe. They may also be gateways to other universes.
It's highly conjectured, but if there's ever going to be a space or a region where you're making connections with, say, some other universe, a black hole in principle could be a portal to that.
In the movies, time travel is as easy as hitting 88 miles an hour, or diving into a black hole.
We've seen the concept of time travel into the past very often in movies and in TV. Did they get it right? Did they get it wrong? It's hard to tell.
So the way that we currently understand time travel in a real sense is through either traveling very quickly or through a gravitational field. All of these things will bring you into the future, but not into the past.
Could physics offer a different route to the past? Stars and planets curve space-time. Black holes bend it infinitely. But strange theoretical objects called wormholes could punch right through space-time, connecting two different points in time with a tunnel.
So if you think about the fabric of space-time is this giant sheet, and you want to get from one point to the other. What a wormhole will do is that it will provide a bridge between the 2 points, making them next to each other.
Travelers would enter one end of the wormhole and exit in a different time, allowing direct access to faraway places. And since wormholes connect points in space and time, they could unlock real-life time travel.
There are some solutions to general relativity that allow for a concept of wormholes, where if you entered it and could somehow survive traveling through it, you would exit the wormhole at a time before you actually entered it, right? So this would quite literally be time travel.
Travelers would need to ensure the wormhole's entry point is anchored in the present, while the exit is locked in the past. Turns out, there's a way to do that.
You take two ends of a single wormhole, a tunnel through space-time between them. Now, you take one of those and you speed it up to near the speed of light. It will freeze in time, by time dilation. On the other hand, this end of the wormhole will continue to travel through time. Let's say in the far future, you want to travel back to the point where those wormholes are created. You just enter this end of the wormhole, the one that's been ticking forward in time, and you'll emerge from the frozen wormhole back where you started from.
But the furthest back you could travel is limited.
You wouldn't be able to go back before the moment you created it, right? So you could create this time machine here and now, and then people in the future could come back to the moment you created it.
A wormhole time machine won't let us go back to Hawking's party unless it was created before the party took place. And there's a bigger problem using wormholes for time travel.
If we found a wormhole and tried to use it to travel backward in time, really the gravitational field would be so strong that it would all just collapse into a black hole.
Of course, you need to survive passage through a wormhole, and to do that, you need to essentially hold open the throat of the wormhole. There's only one way to do that.
To keep the wormhole open requires negative energies. That sounds bad, and it should sound bad. We don't know whether you can make these kinds of negative energies.
People talk about exotic forms of energy that could push apart these wormholes, but we don't know of anything of that sort. The closest we know of is the dark energy that is supposedly accelerating the expansion of the universe.
Dark energy pushes the universe apart, but isn't exotic enough to hold open a wormhole. It doesn't have negative energy. But some scientists hope we'll find something that does.
So first people said weird stuff like that just totally can't exist. But then another kind of weird stuff that we were told couldn't exist, dark energy, turned out to actually exist. So now we're not so quick and fast and loose anymore to just say, oh, are we sure that can't exist?
Someday, we may discover a substance with negative energy, opening up the possibility of wormholes and of traveling backwards through time. But there may be another way to travel to the past, by controlling time itself.
Time itself may be something you can bend and stretch. There may even be different versions of time. So in some respects, time travel may be every bit as real and every bit as strange as our wildest science fiction fantasies.
Time travel inspires incredible journeys of science fiction, and traveling to the past would be the ultimate vacation.
If I could time travel into the past, I would love to experience ancient Rome at the height of the Roman Empire.
I would travel 13 billion years in the past, and I would watch our galaxy form.
Well, I can tell you if I were a time traveler, I would love to show up for Stephen Hawking's party. But is this actually possible? Could we ever travel back into the past?
If we could travel back in time, the possibilities would be endless. But backwards time travel also causes mystifying temporal paradoxes.
Even in science fiction, time travel is all about paradoxes. Is it possible that you can influence your own past? And the most simple way of putting this is the grandfather paradox.
What if you could go backwards in time and kill your grandfather?
In that case, how could your parents have been born? How could you have ever been born?
But if you were never born, then you didn't exist, how did you kill your grandfather? You just run in circles. It doesn't make any sense. It's logically impossible.
It seems like the laws of the universe will not allow you to travel back in time. But maybe there's a loophole.
There could be a way to travel back in time without creating a paradox, thanks to the way that space and time are linked.
Once you believe in four-dimensional space-time, you begin to conceptualize reality as the whole four-dimensional thing, which you then call the block universe. It's like a four-dimensional block of stuff. The different slices are different moments of time.
In the block universe, the past, present, and future coexist.
If you could step outside of this entire framework and see this block universe, you would see the entire history of the universe from time zero to time infinity sitting in front of you.
From dinosaurs roaming the Earth 150 million years ago, to humans colonizing the solar system hundreds of years in the future, and Hawking's party for time travelers back in 2009. In the block universe, all of history exists simultaneously. Astrophysicist Paul Sutter explains.
You can think of the block universe as a film reel, where the past and future already exist. They're just frames on the same film. All the frames already exist. They're just right there, but we experience them in a particular order and in a particular direction based on, a particular turn of the handle.
Just like a handle turning a film reel, time flows from past to future. But since every moment in time exists as a frame somewhere on this reel, then surely we can visit them.
If the idea of the block universe is really true, that makes time travel more understandable and more possible. We just need to find a way to get to different parts of this reel.
To do that, we have to find a way to travel through time. We know planets and black holes curve space-time, but Einstein's equations reveal that really massive objects moving around each other can drag space-time into a loop. November 5th, 2018, an explosive cloud of plasma hits the Parker Solar Probe as it orbits just 15 million miles from the sun.
We have this fleet of spacecraft out there viewing the sun, and they're also under attack by the sun. There are explosions coming from its surface. It's not just light, but explosions of hot plasma. And the Parker Solar Probe got blasted, and yet it survived.
A huge blast of high-energy charged particles launches into the solar system at millions of miles an hour. A coronal mass ejection. But our solar scout is prepared for the onslaught.
The Parker Solar Probe gets very close to the sun, and it has a heat shield to protect it. But if it gets hit by a coronal mass ejection, it has to be protected against that as well. And so it's been radiation hardened to survive such an impact.
Could these blasts pose a danger to our planet?
A coronal mass ejection accelerates subatomic particles, and it's not a little bit of particles. It could be up to 1 billion tons of them screaming across the solar system at high speed. And this is something we need to take very seriously.
To understand these dangerous blasts of plasma, we have to look at their source. An area around the sun known as the corona.
The sun's corona is kind of like its atmosphere. You can think of the sun itself as being a ball of gas, and then outside of that is this ethereally thin gas stretching out for millions of miles.
The corona is a difficult thing to study because the surface of the sun is so bright it blocks our view. We can only see the corona during a total solar eclipse, when the moon blocks the sun's bright glare.
Astronomers, though, we're impatient. We don't want to have to wait for a total solar eclipse, which only happens once or twice a year. So we figured out a way to make an artificial one, and it's really simple.
One member of the solar fleet has it covered. Our solar sentinel, SOHO, creates its own eclipse by obscuring the blinding sun with a circular plate in front of the probe's camera.
Sometimes the best solution is the simplest solution. Instead of trying to make a sensor that could actually see the full dynamic range of the sun's light, why not just block out the light that we don't need?
In July 2012, SOHO spotted a huge chunk of the corona blasting off into the solar system. Seconds earlier, another probe, monitoring the solar surface, spotted a bright flare. Were these events connected?
If a flare goes off, it can disrupt those loops. And if you get the right kind of disruption, the whole thing can just blow open. And then you have a tremendous amount of billions of tons of hydrogen blown off into interplanetary space. And that's a coronal mass ejection.
Coronal mass ejections are solar flares on steroids.
If a solar flare was a firecracker, a coronal mass ejection is more like an atom bomb.
And if a coronal mass ejection comes our way, it hits hard.
The first thing it does is it compresses Earth's magnetic field, and then it wraps around the Earth, and this causes the magnetic field itself to rearrange, reconnect, and streams of particles travel down those magnetic fields toward our poles and impact the atmosphere.
Our shields are up, but they are able to penetrate our shields, our shield being our own magnetic field.
Once they breach our defenses, the particles of a coronal mass ejection can wreak havoc. In August of 1972, tensions were running high in Vietnam.
Two dozen sea mines detonated at the same time when their magnetic sensors were tripped. A satellite was lost because of the electromagnetic pulse that ripped through it.
And an Air Force sensor detected what looked like a nuclear explosion somewhere here on the planet.
Fortunately, scientists quickly found the real culprit. A coronal mass ejection had ripped through the Earth's magnetic field and triggered magnetic sensors. The crisis soon de-escalated.
The sun is an immense ball of plasma 860,000 miles across. We are not going to be able to stop it from doing whatever it wants to do.
What we can do is learn to predict what's going to happen. So we're doing that now.
Our new fleet of solar observers are our first line of defense.
The sun is a little over 90 million miles from Earth. It takes light a little over 8 minutes to get from there to here. As rapidly as a coronal mass ejection is traveling, it still takes a few days to get here.
We can watch the sun to see, is there going to be an event? Or is an event starting? And these satellites can then tell us, hey, you better be careful. You might need to batten down the hatches on Earth.
But there may be an earlier clue the fleet can watch out for. Vast, dark regions moving across the solar surface, called sunspots.
We know that this is the wind up before the release. This thing is getting ready to blow.
In March of 1989, a solar eruption caused blackouts across Canada and malfunctions on board the space shuttle.
We've been seeing some erratic pressure signatures out of Tank 3, as well as some manifold pressure spikes in that system.
11 years later, the sun emitted a flare that was so powerful, it blinded the solar fleet's sensors. 11 years after that, the Earth had a near miss with the most powerful coronal mass ejection ever recorded.
The sun has a very predictable, but actually quite mysterious cycle of activity. It gets very, very active every 11 years, and then it settles back down to more of a peaceful existence.
This 11-year cycle has astronomers scratching their heads. One thing we do know is that violent solar events seem to be preceded by dark patches on the solar surface. Sunspots.
Sunspots are large areas on the surface of the sun, much bigger than the Earth, that are caused by incredibly strong magnetic fields disrupting the flow of plasma.
And every 11 years, these dark spots grow in number, like clouds gathering before a storm.
When you start seeing more and more sunspots, there's an expectation that you're going to see more intense and more frequent solar flares.
But what drives this 11-year cycle?
It's kind of ironic that one of the most predictable things about the sun is also the most mysterious.
We've been puzzling over the sunspot cycle for generations, and now finally we have spacecraft headed to the sun to try to give us some answers.
The SOHO, SDO, and STEREO spacecraft monitor the sun's atmosphere using ultraviolet telescopes. They spot flashes of high-energy ultraviolet light moving across the sun. These waves of light could be connected to the cycle of sunspots and to the sun's outbursts, because everything we see on the sun's surface is controlled by violent processes deep in its interior. Scientists believe an invisible substance is pulling the strings in our universe. But until we see it, sense it, perhaps even touch it, dark matter is just a theory. Sometimes, though, ideas dreamed up by scientists come true. Like black holes. Once the stuff of science fiction and children's nightmares, black holes today are confirmed reality.
So black holes and dark matter have a ton of similarities, right? You know, an unseen collection of matter that creates an enormous gravitational field. Check.
It bends light and causes gravitational lensing. Check.
Test the boundaries of known physics. Check.
It seems crazy to even ask, but could our search for dark matter end in an idea more than 100 years old? Could dark matter be black holes? Black holes appear when stars explode, and their remaining mass crunches down into a sphere so dense even light can't escape its gravity. But that's where the black hole dark matter theory stumbles.
We know that black holes happen, we know how they form, and we also know that there's nowhere near enough of them to be dark matter.
Not enough stars have lived and died in the history of the universe to create 85% of the matter in it. If dark matter is made up of black holes, they would have to be an entirely new type.
It's possible that these black holes are of a type that we've never seen before. They could be primordial black holes.
Primordial black holes are an idea, a theoretical concept at this point that we've never seen, but they could exist.
If primordial black holes are real, then the universe is flooded with black holes.
The smallest could have the mass of Mount Everest packed into the size of one atom. The biggest could be hundreds of thousands or millions of times the mass of the sun.
Stephen Hawking first suggested that primordial black holes could be dark matter back in the 1970s. The idea centers on what happened during that intangible moment 13.8 billion years ago, the Big Bang.
Theory says that primordial black holes formed in the first fraction of a second of the early universe. It's that time between when the universe goes from a pinprick to this giant inflating ball of gas.
In these first moments of the universe's existence, matter is packed incredibly tightly, but it's not quite evenly spread. Even the tiniest fluctuations in density could trigger gravitational collapses. In other words, black holes would be forming everywhere. Theoretically, in huge numbers.
By the time 1 second has passed in our universe, you're already making black holes thousands, hundreds of thousands of times more massive than our sun.
The collective mass of these objects could be vast, but could they be 85% of the universe's matter?
If primordial black holes really do exist, there might be enough to explain the dark matter.
It's a tantalizing possibility, but there's one pretty big problem. For most scientists, the physics of the very early universe is incomplete and hard to trust. Generations of physicists dismissed primordial black holes as myths, fantasies, astrophysical unicorns, until that is, an earth-shaking crash in space. May 2019. A violent cosmic event rocks the USA. How violent? Well, the physical distance between Louisiana and Washington State is stretched by nearly the width of an atom, which is bigger than it sounds. The Laser Interferometer Gravitational Wave Observatory detects this wobble in space-time.
This is the biggest gravitational wave event that LIGO has seen.
This cosmic disturbance seems to come from colliding black holes, but crucially, not the ordinary dead star type.
In this LIGO detection, one of the black holes is 85 solar masses. There's no way that a star could have made that black hole.
Physicists believe there's a range of masses where dying stars can't collapse into black holes. Instead, stars in this zone become insanely hot and rip themselves apart, leaving nothing to crunch down into a black hole. 85 solar masses sits right in the middle of this so-called forbidden mass range. The black hole that LIGO detected can't be a dead star, but in theory, it could be primordial. Could this discarded theory of dark matter be back in fashion?
The LIGO detections come up and everyone says, oh, right, primordial black holes. Maybe we should pay more attention to that.
Primordial black holes can be really appealing because they would solve the dark matter problem. But unfortunately, it's not that simple.
The thing with flooding the universe with primordial black holes is that you expect a lot of collisions. And so LIGO shouldn't have seen one, it should have seen 1,000 of these collisions, and we don't.
Many scientists doubt what LIGO saw was a primordial black hole. To them, these beasts remain fairy tales of physics, red herrings in the quest for solid evidence of dark matter. Does dark matter exist, or are we chasing shadows? Some scientists think it's not only real, but that dark matter is within our grasp, and that it's flying through our bodies right now. We know exactly how the Earth will end. In around 5.4 billion years, the Sun will turn into a red giant, expanding to 1,000 times its current size. The Earth will be destroyed. Humans, if we still exist, will have long deserted our home planet. But how will the universe end?
The age of the universe enables us to not only understand where we came from, but potentially the fate of the universe, what will happen millions and billions of years from now.
If scientists confirm the value of the Hubble constant, the elusive figure that tells us just how fast the universe is expanding, it will tell us the age of the universe, and it will help us predict its end.
Measuring the Hubble constant is measuring the expansion rate today, right now. It's like checking your speedometer at one moment. But just because it's your speed now, it doesn't mean it was the same speed when you left your home or the same speed when you'll be on the freeway.
How the expansion changes over time will control the fate of the cosmos.
So depending on the Hubble constant, the universe could continue to expand, it could accelerate its expansion rate, or it could be decelerating.
At the moment, galaxies are racing apart. A continually expanding universe will cool down as it spreads out.
Another name for this eternal expansion is the Big Freeze, because as everything gets spread out, the density's lower and there's no more opportunities for temperature differences. Everything just gets colder and colder and colder and colder, slowly, eternally approaching absolute zero.
The more matter is spread out, the less chance there is for star formation.
And so the universe's continued expansion means our night sky and every night sky in the universe will inevitably continue to get darker and darker and darker as things move further away and as stars die off.
Eventually, all the stars will go out, and there'll just be the leftovers, which we call the degenerates. Black holes, white dwarfs, rogue planets. It's gonna be a very, very sad place.
The last refuge of any matter at all will be black holes.
You've got a big black hole in the middle of each galaxy. Over trillions of years, everything in galaxies fall in. So finally you're left with big black holes over vast distances, separated almost universes away.
So getting towards the big freeze, black holes themselves start to evaporate. There won't even be black holes at the end of this accelerating universe.
All that's left is very, very low energy photons and a little bit of matter dispersed throughout the universe, and there's nothing left. That's it.
We call that the heat death of the universe. There's no longer any place that has more energy or more heat. It's all just thin, barely there photons.
It's fascinating scientifically, but from a human standpoint, not a lot of fun to think about.
But if the Hubble constant, the expansion rate of the universe, keeps increasing, then the end of the universe could be a lot scarier and come a lot sooner.
One possibility is that the expansion of the universe will accelerate and continue to accelerate forever, faster and faster and faster. And if that happens, we face a scenario that we call the Big Rip, where actually the whole of space essentially just gets ripped to shreds.
So the solar system is going to get ripped apart. Then the sun and the planets themselves will start to get ripped apart. And finally, it works its way down to atoms. And atoms gets ripped apart. And we're starting to see effects on space and time. Space is ripped apart, time comes to a stop.
So in this scenario, time and space have no meaning. If everything is infinitely far apart, then space doesn't really exist. It's sort of beyond our comprehension.
Working out the expansion rate will tell us which scenario we face. But for now, the lifespan of the universe is unknown. Maybe we need to investigate the other end of the timeline. But how can we get a fix on the age of the universe without understanding its origin?
As you go back in time towards the Big Bang, our knowledge of physics really goes out the window.
Temperatures off the scale, pressure off the scale. The way everything behaved is just so different that the rules we have now do not apply.
The biggest problem of all, what came just before the Big Bang? Einstein's general relativity predicts that all the matter and energy in the universe was concentrated down to a single point, a singularity.
The singularity is like the part of those old maps that says, "Here be dragons."
Singularities are a problem. We don't like them. This is where basically you have a finite amount of matter in the universe, but it's squeezed down into 0 volume, so it would be infinitely dense.
Infinite densities don't actually happen in nature. This is a sign that our math is breaking down. This is a sign that we need to replace that with a new understanding.
Many now believe Einstein was wrong. There was no singularity, begging the question, could the age of the universe be infinite? Scientists investigating the age of the universe are struggling to understand its origins. Could that be because there was no beginning? Could the universe be infinite?
Because we think we live and we die, we project that onto the universe. But that may not be the case.
The idea of an infinite universe is no more strange than the idea of a singularity. And in fact, throughout most of history, astronomers thought that the universe was probably infinite.
The foundation of our mathematical understanding of the universe, Einstein's general relativity, has a problem. It doesn't translate to the world of the very tiny, which is why its laws break down close to the Big Bang.
General relativity does a great job at describing things on scales that you and I are familiar with, and things like how planets move and how galaxies evolve, all the big stuff. Quantum mechanics, on the other hand, describes the world of the very small, the world of the atoms. The problem is that these two theories don't fit well together at all.
A new theory, known as loop quantum gravity, brings quantum theory and relativity together, and it makes a stunning prediction.
So one possibility is that the end of the universe could kind of match onto the beginning of a new universe and create a cycle of universes one after the other.
Nicknamed the Big Bounce, it predicts a universe that stops expanding and switches into reverse.
And the idea here is that the universe can expand for a time, stop expanding, and then begin to contract again. And some have suggested that perhaps there's a cycle of expanding and compressing. It bounces back over again.
One of the appeals of the bouncing model is that it allows us to get beyond the singularity.
A bit like recycling on Earth. All the components get crushed down and then reused, giving the cosmos no beginning and no end.
If the universe is cyclic, does the age even have a meaning?
Age is a construct of humanity because we need to count time. But if the universe is infinite, maybe it doesn't matter in the big scheme of things.
A contracting and expanding universe messes with the concept of age. But the very idea of an expanding universe provides another cosmic curveball. It might not be alone. It might be just one ageless universe among many. It's an idea embedded in the math of the Big Bang. We're taking our seats for the most violent event in the universe, the collision of two supermassive black holes. We've never witnessed this cosmic heavyweight championship, but we can build up a picture of this epic fight by studying other weight classes with lighter fighters. (2020). The Earthbound Gravitational Wave Detector, LIGO, picks up the distinctive signal of a stellar mass black hole merger.
What we saw was a black hole of 85 times the mass of our sun and another black hole of 66 times the mass of our sun smashing together to create a combined black hole.
As someone who studies black hole mergers, this was a really exciting event.
We're talking about the largest, the heaviest, the most massive black holes we have seen collide to date.
It may be the largest detection, but on a universal scale, it's still a small fry. Like lightweight boxers, the two black holes circle each other and emit low-energy gravitational waves. This energy loss causes the black holes to spiral in together. Finally, they collide in a cosmos-shattering event, forming a single black hole and releasing a huge blast of gravitational waves. But when astronomers examine the single merged black hole, something doesn't add up.
If you take the combined mass of the two black holes, you get to 150 times the mass of our sun. But actually, the black hole that's left only has a mass of 142 times the mass of our sun.
So the mass you have before the event does not equal the mass you have after the event. What happened to that missing 8 solar masses?
The way these black hole mergers work is very roughly 5% of the total mass of the system gets converted into energy.
It all comes down to E equals mc squared.
This is that beautiful equation that Einstein told us, E equals mc squared. E is the energy and m is the mass.
Einstein taught us that mass and energy are related. In fact, much of what we call mass is actually energy.
In this case, the violence of the collision transforms 18,000 trillion tons of matter into an explosion of gravitational waves.
In just a fraction of a second, 8 suns worth of matter is converted into pure, unadulterated energy.
The amount of energy released was so great that if you add up all the energy of all the stars burning in the universe, it was bigger than that.
This event was a collision between relative lightweights, 2 stellar mass black holes. To understand heavyweight bouts, we need to scale up to supermassive black holes.
In the universe of sports, supermassive black holes are the heavyweight contenders.
With these big black holes, size matters. The bigger, the better.
More mass means more energy, which means more destructive power.
We don't need to look too far to find this devastating muscle. This is M87 star, one of the largest supermassive black holes in our cosmic zip code.
M87 star is huge. It weighs about 6 billion solar masses, about 6 billion suns, and it's the size of our solar system.
A collision between 2 6 billion solar mass supermassive black holes would release around 5 times 10 to the power of 56 joules. So, what's that mean in real-world terms?
It's hard to use words to express how much energy this is, and the numbers are so huge, they're almost meaningless. The only way I can really explain this is...
In physics, we have these comparisons so we can get a mental picture. But for something like this, there is no mental picture. That is so freaking big.
So where does this destructive mass and energy come from? It starts with the simplest ingredient, hydrogen. Hydrogen is the basic building block of the universe. Each atom is tiny, but it contains a lot of energy.
Hydrogen atoms contain a huge amount of energy, just like all matter does. And if it's unlocked in a certain way, there can be huge explosions.
I mean, you take the mass contained simply in my hand and you could blow up pretty much the entire Earth.
Matter has energy because it formed from energy in the early moments of the universe.
In many ways, atoms are reservoirs of stored energy from the Big Bang.
13.8 billion years ago, the universe ignites in a super hot ball of intense energy.
Right after the Big Bang, there's a tremendous amount of energy. So much energy, in fact, that normal atoms can't exist.
As that early energy starts to cool, it can start to form primitive matter.
The universe takes that first matter and energy in the form of hydrogen atoms and starts the process of creating a supermassive black hole. Step 1, build giant stars.
So gravity brings together gas, dust, hydrogen, all of that stuff. And as the clouds become more dense, they attract even more material.
As they spin, they get hotter and hotter. And as that temperature and pressure increase, finally it ignites nuclear fusion within the core and creates an actual star.
These huge stars are like cosmic rock stars. They live fast and die young. When they die, they flame out in a huge explosion, a supernova.
The entire star turns itself inside out and releases a shock wave going a good fraction of the speed of light and releases enough energy to just obliterate you.
If the dying star is more than 15 stellar masses, its core collapses into a black hole.
It's kind of astounding what the universe is doing. It's taking incredibly simple things like hydrogen atoms and using gravity to ultimately bring all this stuff together and make things like black holes.
I find it quite beautiful how our whole cosmic history is the story of little things coming together into bigger things.
But these stellar mass black holes are tiny flyweights. To step up to the heavyweight division, they have to grow billions of times more massive. But how?
How do black holes become supermassive? This is the age-old question. We're not really sure.
The current state-of-the-art understanding of how black holes become supermassive is like, we're confused, really don't know.
We still don't know exactly how they become so big.
But we do know that the process involves ultraviolence, death, and destruction. December 2018. Astronomers spot strange flares coming from a galaxy 250 million light years from Earth. GSN 069.
We know that GSN 069 has a supermassive black hole in its center, equal to about 500,000 times the mass of the Sun. That's a big black hole. And it blasts out X-rays in a very, very steady pace every 9 hours. Why?
The flares are so energetic and regular, the supermassive black hole must be eating the mass of the planet Mercury 3 times a day.
The big question is, what's feeding this black hole such a huge dinner?
In March 2020, scientists found the answer. An unlucky star at the end of its life had wandered into the death zone of the black hole.
A star getting too close to a supermassive black hole is like a glazed donut getting too close to me. That thing just is not gonna make it.
Stars that get too close to a black hole get torn apart. They sort of get attacked by the black hole, and some of that material is also getting launched off in very powerful winds and jets and streams getting out.
Somehow, the star survives its close encounter with the supermassive black hole. Further investigation reveals it's a small, compact star, a white dwarf. So what makes this tiny star almost indestructible? The answer lies in how it's formed.
We get a clue if we look at the life cycle of a star. It's burning hydrogen into helium, that's causing nuclear fusion, and that causes a star to stay stable. There's this delicate balance between radiation pressure from that nuclear fusion pushing out and gravitational pressure pulling in. But when stars like our sun near the end of their life, they run out of hydrogen fuel.
The sun-like star makes more and more helium, which builds up in its center. Gradually, the immense weight of the star's outer layers crushes the helium core.
As the core ages, it gets smaller and hotter, which increases the rate of nuclear reaction.
These nuclear fusion reactions produce more energy, which pushes the outer layer, or envelope, outwards.
Because there's more energy flowing through the envelope swells up.
The star expands to around 100 times its original size. The yellow star becomes a red giant. Eventually, red giants shed their outer layers, forming stunning gas shells called planetary nebulas.
Planetary nebulae are the most beautiful objects in space. They're all spectacular.
A star that ends its life in one of these planetary nebulas leaves behind a white dwarf at the center. And this white dwarf is essentially a cinder, a stellar cinder.
It's what's left after nuclear fusion is no longer possible for that particular star.
All that remains, a glowing white dwarf, the leftover core of the dead star. But in galaxy GSN 069, the supermassive black hole turbocharged the process. It stripped off the outer layers of the red giant in a matter of days.
The black hole has almost eaten all the juicy parts, all the easy-to-get-at parts of the star, leaving behind the sort of bone or the leftovers of the white dwarf.
This white dwarf is just a fifth of the mass of the sun. How can such a small star survive, being so close to a black hole?
You might think that because a white dwarf is small, it's not going to last very long because there's not that much stuff there to eat. But it turns out it's quite the opposite.
The pocket-sized white dwarf is packed full of matter.
If it were a normal star, it would have been shredded long ago. But because it's such a dense, tight ball of matter, it survives. Imagine taking the sun and crushing it down to just about the size of the Earth. Same mass, but now packed way more tightly. So a basketball worth of this stuff would weigh as much as 35 blue whales.
The white dwarf's extreme density protects it from the gravitational onslaught of the supermassive black hole.
Its orbit takes it near that black hole every 9 hours, and every time it encounters the black hole, some of its material gets sipped off.
They're playing a game of interstellar tug-of-war with one another. The black hole is bigger, so it's going to win. But the white dwarf is very dense, so it's very tough, and it's able to hang in there for quite a long time.
It's gonna stay in orbit around a supermassive black hole for billions of years. Talk about David and Goliath.
When astronomers first discovered white dwarfs, they thought they shouldn't exist. How could something have such an extreme density and not collapse under its own weight? Quantum mechanics, the science of atomic and subatomic particles, has the answer.
We're used to the rules of physics up here in the macroscopic world. But when you zoom down into the subatomic world, things get weird. Here we have the electron, one of the tiniest particles in the universe, and it's these little electrons that are doing the work of supporting an entire star.
Electrons really don't like being squashed into a small space. If you try to squash too many of them into too small a space, they'll push back really hard, and this is an effect called degeneracy pressure.
These degenerate electrons stop white dwarfs from collapsing. But they give these stars strange qualities.
White dwarfs behave very differently than normal matter. Take planets and stars. They become bigger when they gain mass. White dwarfs are the exact opposite. As they gain mass, they get smaller.
The more massive a white dwarf, the tighter the electrons squeeze together, and the smaller and denser the star gets. The high density means the white dwarf's structure is also strange. It has an extremely thin atmosphere made of hydrogen or occasionally helium gas.
If you were to take an Earth skyscraper and put it on a white dwarf star, if you climbed to the top of that skyscraper, you'd be outside of the white dwarf's atmosphere. You'd actually be in space.
Beneath the thin atmosphere lies a surface of dense helium, around 30 miles thick. It surrounds an interior made of superheated liquid carbon and oxygen.
A white dwarf at its surface can be 500,000 degrees. It's even hotter in the interior. And so that kind of material, it's not going to behave the way normal matter does.
Eventually, over billions of years, the center of the white dwarf cools down into a solid.
As the carbon and oxygen atoms cool down, they form a crystal. Diamonds are actually crystals of carbon. So at the center of these cool white dwarfs could be a diamond the size of the Earth.
White dwarfs gradually give off their remaining energy until there's just a cold, dead ball of matter, a black dwarf.
We've never seen what we call a black dwarf, and there's a simple reason for that. It takes a tremendous amount of time, many tens of billions of years, longer than the age of the universe to reach that point.
This is the dark destiny of most mid-sized stars, including our sun. This long, slow death may make white dwarfs seem ordinary. But these tiny stars could answer some big questions about our universe.
They might be small and they might be dim, but they are essential for our understanding of physics.
New research into white dwarfs may answer one of the biggest questions of all. Can life survive the death of its star?